So I'd like to go ahead and introduce our speakers for today. First off, we have Mr. Tom Bronze. He is the Honeywell Customer Marketing Manager, and he provides technical support for sales, pressure, temperature, and flow products. Previously, Tom worked as a wireline engineer for Schlumberger off the coast of the Gulf of Mexico. He has held several roles with Emerson Process Management, including product sales, business development manager, regional sales manager, and so on. He also worked for GE Panametrics as a sales manager and in industry marketing. Tom actually grew up in New Orleans, where he earned his bachelor's degree in physics from Loyola University. Our next speaker that we'll have today will be Mr. Ned Espy, our technical director here at Beamex, and he has actually been promoting calibration management for over 20 years. He's helped develop best practices for calibration with a focus on pressure, temperature, and multivariable instruments. He's a consistent editorial contributor to leading industry publications and has received significant recognition within the automation industry. And today, Ned teaches calibration best practices and provides technical support to end users and the Beamex sales team in North America. Next up, and finally, we have Mr. Roy Tomalino, who's been teaching calibration management for 14 years. Throughout his career, he has taught on 4 different continents to people from over 40 countries. His previous roles include technical marketing manager and worldwide trainer for Hewlett-Packard, as well as an application engineer with Honeywell. Today, Roy is responsible for all Beamex training activities in North America. So with that, I'd like to go ahead and hand it over to Mr. Tom Bronze, who will start us off with the agenda and continue on with the presentation. Take it away, Tom.
Thank you, Katie. So this will be how to calibrate temperature instruments part 2. And in this session, we're going to cover several different applications. We'll talk about heat exchangers first. And we'll sort of spread the applications throughout the session. We'll have a live demo, go into some more advanced type of calibrations. And then we'll talk about some theory, loop calibration concepts. We'll have a Q&A session. And then we'll do a second application, measuring temperature in autoclave. We'll have another demo. And we'll talk about a third application, measuring temperature in a refinery. Ned will cover infrared temperature measurements. We'll have another demo, we'll have the conclusion, and finally a Q&A session. So I'll start this out with our first application, which is temperature measurement in a heat exchanger. This is a pretty common piece of equipment that you'll see in pulp and paper mills, in chemical plants, in power generation, petrochem, refining, and so forth. But a heat exchanger is simply a way of taking one fluid and either making it hotter or colder. So this is a look at a shell and tube type heat exchanger. So the liquid that's going to be either heated up or cooled comes in through the header, runs through the tubes, and then comes out at a different temperature. So the heating or cooling fluid goes in through the top connection, flows out through the bottom. So for this, let's talk about right now cooling off a liquid. So at a polyethylene plant, you'd send in a hydrocarbon through the head, through the plenum, and then that would flow through the tubes, and then cooling water would flow over the tubes, come out through the bottom, and then the hydrocarbons would come out the other end at a colder temperature. So an application for measuring temperature in a heat exchanger is trying to detect fouling. So fouling might occur on the outside of those tubes because the cooling water, in our polyethylene example, the cooling water was running on the outside of the tubes, and that could result in scaling on the outside, or fouling can occur on the inside of the tubes. So that's going to restrict, if the fouling occurs on the inside of the tubes, that'll create a pressure drop across the heat exchanger. It's going to restrict the fluid flow, and of course it's going to affect heat transfer. So that's going to result in reduced thermal efficiency. It decreases the heat flow, the heat flux, and one temperature application here is to measure the difference in temperature from the inlet to the outlet. So this could be at where the fluid is coming in through the tubes. then measuring the temperature on the output and comparing those temperatures, getting a differential temperature. And if that differential temperature gets too high, that may be an indication of fouling. Likewise, you could measure the differential temperature of the fluid that's flowing on the outside of the tubes. Okay, so if there is fouling and you're not able to detect, this could result in constrained throughput, the lost production, or frequent and costly kind of repair, particularly if it's unexpected. At this point, I'm going to turn it over to Roy for a demonstration.
All right, hopefully you can hear me now. What we have here is a calibration of a temperature element. We're using a dry block, and I'm going to make you dizzy just for a second. Let me grab my camera and show you what I have going on here. I've got my MC6 calibrator, and it's set up to do a test here, and I'll show you this on the screen. Next to it, I've got my temperature source. In top, I have my temperature element under test. That's the one on the left. Then I have a PRT, a reference probe, on the right to make the dry block more accurate. And I've got this all connected through a cable here going over to the MC6. So the calibrator is controlling the dry block, telling it what temperature to hit, and grabbing the temperature values at each step in order to do the calculation. On my screen, you can see my calibrator itself. On the input, we're getting the input from the dry block, and I'm measuring the RTD, and it's showing me where to plug in, so I'm connecting on these left-hand connections. If I hit the check mark, now I've already had this thing running, and it's already cooled down. The test goes from 32 to 212, or from freezing to boiling. And let me hit the start button. We can see our green dot here, and we've got a 5-second countdown, so it's about ready to accept this test point. We have negative 0.172 degrees of error or difference in between our probe under test and our reference probe. Now the dry block is heating up, so we'll get to the next temperature, which is in the middle, 122 degrees. So while that's heating up, I'll show you something else, and then we'll come back to this demo a little bit later on. But first, let's go to YouTube. In YouTube, if you type in Beamex, you can get to the Beamex channel. So here's Beamex calibration, and well, actually, here's the Beamex 40th anniversary. We turned 40 this year. Under Beamex calibration, there are a number of different videos, and these are how-tos in different scenarios. Okay, this is weird. I'm hearing and seeing myself talk here. In this example, this is a video of how to calibrate two different sensors at the same time. This is using two thermocouples. No, it's not. Two dry blocks. We're testing a thermocouple and an RTD. These could be going to the same transmitter as a dual sensor, but this example is testing the two elements themselves. So we're calibrating a thermocouple and an RTD using one calibrator with the push of one button, because the entire thing is automated. And you can check that out by simply going to YouTube. I'll show you a few other examples that have to do with calibration on YouTube as well, just because it takes so long for the dry block to ramp up and down. But with that, I'm going to hand it back over to Ned.
So that was Roy's demonstration. We're going to change channels a little bit here. And Roy kind of touched on it, but I want to talk a little bit about loop testing. So this is a very common practice with temperature. You know, it's one thing to test, as in this drawing here, the temperature element or disconnect the element and check the transmitter. You might disconnect the local display and you can shoot a signal into the DCS and so on. But, you know, when you look at a loop, which is a group of instruments that are making a single measurement within your process and that affects some type of control action, really what matters in your process control is what is the DCS display, and is it displaying true temperature as measured by the temperature element at the other end of the loop. So I've come up with I've coined the term an end-to-end test would be best practice. So you would want to exercise the probe and compare your traceable test on the probe to the DCS display. Sometimes that's not practical. It may be difficult to pull the probe out of service where you can drop it into a dry block or a bath. So you may have to make a slight compromise and break into the loop. So here we are disconnecting the temperature element for the partial loop test. We would shoot either ohms or millivolts into the transmitter and compare that to the DCS. And if you do have to make a partial loop test, it would be great or best practice if you could also do some kind of single point check on the temperature element that's in the process. Maybe you can have an extra thermal well or have a way to insert a thermometer temporarily into the process to make a comparative measurement and just verify that the element's in good shape as well. So those are the two types of ways you can try to test using a loop approach. And even though you're not checking the transmitter and the local display, as long as the end-to-end result is accurate, there's really no point in checking it. If during your testing the loop is out of spec, then you would maybe break the loop down and perhaps the transmitter is drifted. You could make a trim on that and it would bring the total loop back into good operation. When you look at a loop test, there are some considerations that you need to apply when it comes to what is the total loop error. So here's an example where you have an RTD sensor, transmitter, and the DCS input card. All three elements drift, can change, and have a measurement accuracy. So the RTD sensor, in our example, maybe it's within half a degree. The transmitters are pretty good today, and with a span of 50 to 250 as an example, you could say that's 0.1% or 0.2 degrees. The DCS input card might be slightly higher, might be the same. But if you look at these three numbers, the weakest element in the loop would be the sensor, the half a degree error. So how do you analyze the accuracy of the loop? One method in metrology is to use an RMS statistical average. So if you square each value, and in this example, I'm changing everything to degrees F. If you square each variable, add them together and take the square root, instead of a half a degree, which is the weakest link here, the other two elements, the transmitter and DCS input card, would add an additional quarter of degree uncertainty or error to the measurement. So maybe that's the best you could expect out of this loop. Maybe you'll set a pass-fail on the loop of 1 degree. Just give yourself a little breathing room. And some people don't like the RMS method. So for those of you out there that don't like doing an average or maybe you think it's a game to use statistics, you could simply add the errors together. So if each component had drifted to the max in the same direction, this loop would be off by a potential 1.2 degrees. So maybe you'd set your tolerance to 1.5 degrees or even 2 degrees. So that gives you just some ideas that you need to consider that the loop is only as accurate as the weakest element making the measurement. And to kind of wrap this up, what are the benefits of doing loop testing? Well, it's really good that you're not breaking into the loop and disturbing all the different wiring connections and components. You could miswire things when you put it back together. You're going to have an increased confidence in your measurements when you're doing loop tests. There's going to be less arguments, less disagreements. With a loop test, as I mentioned, you're touching, in this case, 2 or 3 instruments in our example, all at one time. And there's really, you're not making unnecessary tests if the loop is checking out. And it's also something that if you're doing a lot of temperature loops like this, your personnel is going to have really sort of good standard practices. Everything's going to be repeatable, and you're going to get some efficiency gains. And if you're having to, document this, you can start analyzing your test cycles. And if your temperature measurements are staying within control, why test more frequently than necessary? So you can look at your intervals and maybe make some gains there. But the bottom line is you want to deliver quality information to the control engineer. So you want to give the control folks the very best measurement that they can get. Okay, so that kind of wraps that up. And before we turn it over to a question session, we did have a poll we wanted to ask the audience here. Let's see. And we just talked about loop testing. I'd like to get your feedback. Our panel would like to get your feedback on if anybody out there is doing loop testing. How many of you are doing it? So hopefully you guys can see this. And, please, this is sort of instantaneous. I'm going to close this up in a minute here. But we'd just like to get a feel for how many of you are looking at loop testing or utilizing this technique in your facility. So already half of you have voted. We appreciate your participation here. I'll close this off as we get a little bit more participation, and I'll share the results with everybody. So it looks like it's kind of balanced where we've got about a third of you out there doing loop testing and doing partial loop testing, and then a third of you have never done it. So very interesting. So we're up to 74%. Looks like it's slowing down. So I think we've got a good representation here. Let's, I'm going to close this off. Thank you for participating, and let me share the results with you now. So yeah, this is very interesting to me. I'm glad to hear that a significant amount of our viewers are using some type of loop approach. Looks like 70% have utilized this technique. And so, I guess one thing I want to mention is I did publish an article on this, and it happens to be in the latest issue of Intech. So that is on one of the handouts is a link to how to get that paper. So maybe, think about this, and, you can utilize it more in your process, or for those that aren't using it, maybe it's something new you can take a look at and implement this if it can help you, make better quality measurements and also possibly save you time. Okay, so with that, why don't we open it up for some questions?
Excellent. Thank you, gentlemen. The first question we have here is, Mr. Roy, is it possible to rectify an RTD or thermocouple which shows a nonlinear variation from the real value?
So a nonlinear, I'm going to say no. The only thing you can really do to a probe is to anneal it to help bring it back. Ned and Tom, do you have any input on that?
I can.
Go ahead, Tom.
Yeah, I can speak a little bit to the RTD. RTDs are, well, this is really prior to using an RTD that you'd go through this, but RTDs are pretty linear, but they're not perfectly linear, and that's because of variations in the purities of the platinum that go into making them. And because, since they're not perfectly linear, the manufacturer can actually do a linearization before, during the manufacturing process. And that's the constants that result from that are called calendar Van Dusen constants. So if you wanted to buy a linearized RTD, you could do that, but you'd have to order it that way. And when you get the RTD, it would come with a tag that has your calendar Van Dusen constants on it, and that's something you didn't put into the transmitter. I'm not aware of anything for thermocouples.
Yeah. Also, Tom, in addition to calendar Van Dusen, there's also ITS 90 coefficients that are maybe more in vogue today, but both are ways to get more out of an RTD. I would say if the probe is not linear, I would throw it away. What happens to temperature probes, in my experience, is there's a zero shift. If it's been shocked or somehow thermally shocked or physically shocked, dropped or somehow damaged, usually there's a zero offset. You'll see a zero shift. And so the only corrective action you could take in that case is if you sort of decalibrated the transmitter that it's connected to, you could, impose a zero shift on the 4 milliamp end, and it could still make a good measurement. But yeah, I would say if the sensor is nonlinear against its curve on a calibrator, that there's something going on. You probably should replace it if it's significant.
All right, very good. Next question is, in error analysis, isn't RMS actually RSS, root sum squared? Is there a probability associated with that calculation? For example, 95% confident.
Yeah, I guess, I'm not being a pure mathematician or statistician in my explanation, but, when you're looking at loop error, you just want to be kind of in the ballpark and have some confidence. So, so RMS or root square sum isn't the end-all way. It's just one way to analyze the potential error. So, with my root mean square example, I'm just assuming that the transmitter might drift a little high, the probe might drift a little south. If they're all drifting in different directions, you might have zero error at the end of the loop. So it seems unfair to do the conservative added up approach. So if you want to have a higher level of confidence, then just add the errors together. But I personally feel the RMS, just summing the squares, is a fair way to analyze and make a good educated guess on what the error might be.
Very good. Next question is, can we have a PDF to study on the loop testing? And I would answer that by saying that you could read this month's edition of InTech that Ned referred to earlier, where he has written an in-depth article on loop testing. It is also available on the handout section of the GoToWebinar nav bar. There is a handout that's called temperature links, and in that you'll see a short description of the article, and if you just click on it, it'll take you to the full article itself. Are there any other resources you guys can think of at this time?
No, I was taught loop testing by a customer 25 years ago, so it's something that's been around a long time, and I think it's just underutilized. It's a good technique.
All right, very good. Next question is, what are the differences in calibration between an RTD and a thermocouple?
Roy, you want that, or I'll?
Well, as far as differences, it's pretty much the same thing. They have different they operate differently, but calibrating them, you're still using a raw temperature, or you're simulating millivolts or resistance to simulate the actual probe itself to go into a transmitter. What else were you going to say about that, Ned?
I was going to say, I can totally concur. I would say in terms of the approach, it's the same. It's, you know, thermocouples have a higher temperature. With both of them, I would tend to do a low, medium, and high temperature, just 3 points. There's really no need to go up and down. You know, if it measures 100 degrees at the start, and then you were to go do a cycle to some high temperature and come back to 100 degrees, it's going to read the same number at 100 degrees if you let it soak out. You know, and you don't need to, you know, you need to, the test points you pick need to match your process. You don't need to go beyond the process, even though the probe can handle it, or go freezing if your process never goes cold. That'll just save you time.
Agreed. So how many test points would you do? Let's say that your probe actually goes up to 1800 degrees, but your process temp is 600. Would you put in 2 test points then between the two, or would you go to 3?
Yeah, I would do, you know, like 100, and then I guess 350 and 600, so, you know, something like that.
Part of the goal is to develop numbers or statistics to see if we're looking at a linear values between the different temperature readings.
Right, and of course on the application, if you're doing something where temperatures are really critical around a specific point, you know, maybe you could do some extra test points, you know, 10% lower than the critical point, and then 10% above the critical point. You know, why bother checking it at low end and high end, you know? So there's different approaches you could take.
Okay, very good. We have probably time for one more question. How can we transfer the calibration tool rating to the DCS/BMS?
So that's the, what's TUR, Roy? It's test uncertainty ratio.
Yep.
So read that again, Katie.
It says, how can we transfer the calibration tool rating to the DCS/BMS? Do we need a little bit more clarification on that question?
I'm not exactly sure what's being asked here.
Okay.
I think I can make a comment or a guess. To me, when you're trying to set your pass-fail, your process tolerance, there's a lot of discussion on that with our customers. And Tom, I'm sure you run into it as well with your customers, is, you know, people are trying to use the stated accuracy of a transmitter or something like that as their pass-fail. And I'm a big proponent on going to the control engineer and what kind of temperature control do you need to make good product or to get high efficiency out of your system. Those kind of, you need to take a more practical approach. By making something very tight and it's maybe unrealistic, and you know, you also need to consider long-term stability of the instrumentation. You know, people state an accuracy, but there's also a stability component usually stated, and you can't ignore that if you're testing once a year or every 6 months or something. So, so try to balance what the manufacturer specifications are with what is good, what kind of temperature control would, you know, deliver good product and good quality.
And just one side comment on that. At the ISA symposium in Houston just a week or so ago, we did some calculations, and from a safety perspective in this one process, they were calibrating to within 0.25% or even tighter, but from a safety perspective, we found out they could even be 10% off and still be completely fine from a safety perspective. So that just, I think, supports your comment about having your tolerance based around your process needs and not just on the accuracy of whatever you're using.
Yeah, because to make a 1/4% measurement could be very expensive. You might have to get a reference probe that costs, several $1,000s altogether, and you got to maintain that and take care of it. And if you could stand 1 degree or 2 degrees, it'd be much more practical to maintain as well as be safe.
Right.
Okay, we got a couple more comments from the person that asked that question. BMS stands for Building Management System. And as a follow-up question, he says, so the calibration tool does not have an interface port, am I right? So I think he might be talking about uploading it into the software directly.
So when I get done with this calibration using the MC6 and the dry block, the data will be on the calibrator, and I can unload it directly into some calibration software without using a pen and paper. So that will all be automatic if that's what you're getting at.
Well, and you can also, you could go into your BMS system and make an adjustment to where true temperature is displayed over the test you just made. So you could, that's a way to improve the loop measurement.
Yeah.
Okay, very good. We have a whole lot more questions, but we're going to go ahead and conclude this question and answer session to be sure that we get through the materials that we have to present to you all. Any questions that we didn't get to, again, they will be held till the next session, so don't worry, your question will be answered. With that, I'd like to go ahead and hand it back over to Tom to take it away from here.
Okay, thank you, Katie. Before I get into this next application, a last comment on the previous application with heat exchangers, I didn't mention this, is that when you're trying to measure differential temperature, say across a heat exchanger from the inlet to the outlet, heat exchangers are relatively small compared to a lot of other assets that we're measuring, but it's possible to use two sensors into one transmitter to get to differential temperature. So that's, these sort of, features with temperature transmitters allow you just to use one temperature transmitter with 2 sensors instead of having to use 2 temperature transmitters. Okay, so with that said on heat exchangers, let's move on to this application with an autoclave. So an autoclave is a special apparatus where special temperature and pressure conditions must be maintained. It could be a lot of different applications like curing in general, and I'm going to talk about a specific curing kind of application that could be used for sterilization as well. So I'm going to talk about curing of composites, and there are a lot of different kind of composites that are cured in autoclaves, but I'm going to focus on sporting goods because that's a lot of fun, right? So it could be things like golf clubs, could be shin pads for soccer players, and I'm a cyclist, so some bicycles are made out of composites, carbon fiber frames. So some of them are made of lightweight aluminum or lightweight steel, but the carbon fiber by far are the lightest. They're pretty stiff, but they're definitely the lightest, and they cost more. So I said here curing is a 2-step process, but it can be more than 2 steps. So the composite material is cured. What it does is the autoclave ramps up to a certain pressure and a certain temperature, and that's for a predetermined amount of time. Then it goes to a second level. And the composite material is made up of an epoxy resin, and it would have some sort of fiber in it, maybe a carbon fiber. And they call this a pre-preg, which means pre-impregnated. And the composites are typically a thermoset, which means that once you heat it up and cure it, it's done. You can't melt it back down and try it again. So it's important to get this right. And it's important to get, on this third bullet, you can see it's important to get this uniform temperature distribution. So imagine if you're making a bicycle frame and one part of that frame does not cure correctly, that's a weak spot. And of course, could be pretty dangerous for the rider. In the bottom right, you can see the mold in which they would develop this bicycle frame. So each one of these different materials or objects that are cured in an autoclave has a different recipe having to do with the temperature, the pressure, the amount of time, the different stages, and so forth. Okay, a little bit more. Here's a look at an autoclave. And temperature measurement is obviously very important for this. So temperature sensors are monitoring the temperature of the air around the part, the temperature of the part itself. And these are what are used in the cure cycle as part of the recipe. So there's a controller that runs the batch, there's a data acquisition system, and there's diagnostics that typically go along with it. Diagnostics to check the health of the sensors to make sure you're getting a good reading. Now, a bicycle frame is relatively simple, it's kind of small, but imagine much larger parts. In those cases, you still want to maintain that uniformity of temperature across the part. And some of these autoclaves are set up into different stages, and each one has different ducts, fans, motors to control the temperature. And that is, again, there to make sure that you get a uniform cure across the whole part. So they can get kind of complex as you've got these different stages within the autoclave, and it can involve quite a few temperature measurements. And you can see that drawing sort of in the bottom right of the slide, and it's showing a vacuum bag along with the thermocouple, the part itself, and the vacuum bag is there to pull as much air out as possible because you don't want air bubbles in that epoxy resin as it's curing. Okay, so temperature measurement very important with autoclaves. All right, I'm going to turn it back over to Roy.
Are you sure you want to do that?
That's what I'm supposed to do.
Yeah. All right, that kind of hurt. So back to my calibration. You can see the MC6 on the screen, and we're at our middle test point. We're going 32 to 212. Again, it's freezing to boiling, and I'm just doing a 3-point test from that range. And let me hit continue. I had paused it so it didn't go because this is set up for an automatic calibration. And I've only got a 5-second delay set up in between these steps, and I would probably put a 3 to 5 minute delay just so there was more time to stabilize the temperatures. So it's just grabbed our middle test point, and we can see that, boy, that's right on the zero. We're at our midpoint, there is relatively no error. The tolerance that I have on this is a rather large 1 degree Fahrenheit, plus or minus. So that's what the blue dotted lines represent. If my temperature were outside of that 1 degree error, then it would turn red like you're seeing on the screen right now. And while that's going on, let me show you another example of what you might do in an autoclave scenario. So back to the videos, and if you do go to YouTube and go to the Beamex channel, you'll see a couple different categories. One of them is called Mike's Calibration Corner. Mike is a colleague who is in England, and he's got a number of videos out here. One of those is how to calibrate an 8-channel transmitter. And I'm not going to play this because the video would end up being too choppy, but you can go out here and check this out. This video is called How to Calibrate a Multi-Channel Field Bus Transmitter. And you could do this yourself with, if it were a multi-channel heart, it doesn't matter if it's field bus or not. And we have 8 different temperature sensors plugged into that dry block at one time. So we had a special insert created, and we drilled 8 identical holes so we could have them all in. So when we go to our first temperature, we have 8 different tests or 8 different functions, and we can grab them all individually. So we grab test probe 1 at the first temperature, then we grab test probe 2, and just go around in a circle until we've grabbed them all. Then we increase the temperature in the dry block to our next test point and grab the temperatures all the way around until we've achieved our second test point for all the probes. Now, because this is field bus, it automatically pulls out the process variable into the calibrator. If you were doing a multi-channel with heart, you would have to swap the leads for each temperature probe. There is a company that does create do this all automated wise, but so that is a possibility. So one other thing, back to the videos before I relinquish control, there's also Roy's Calibration Academy. And if I click that, it'll show the different videos within here. You know what, let me just go to the video section. This will show everything that we've got out here. And they go from a couple minutes to, I think, 10. So they're all designed to be pretty short. And then we also have copies of different webinars as well. So this is what I'm interested in right now, is how to calibrate an analog temperature loop. So I'm going back to where Ned was speaking previously on calibrating things as a loop. Let me go to where I'm actually plugged in here. In this case, we have a temperature transmitter. This one happens to be hard, so we want our 4 to 20 output. And it's a loop because we have our temperature probe plugged into the dry block that you can see, and that's connected to our transmitter, which gives us our 4 to 20 milliamp output. So we're literally testing the temperature on the input, and then we're comparing that against the milliamp output to see if there's any error that needs to be adjusted. Now, if there is error, we can trim it on the transmitter itself, or to the question that was asked previously on the control system, you could enter in an offset in your control system to remove any offset that's inside the probe or the transmitter. So that would work as well. All right. I think we're muted. We not have...
Is that better?
Perfect.
Our third application is measuring temperature in a distillation column in a refinery. So just a little background. The crude oil is a mixture, actually, hydrocarbon. So it's a mixture of different molecules, different combinations of carbon and hydrogen. So the carbon is heavy, hydrogen is light. So the molecules that contain just a lesser amount of carbon, like methane, just has a single carbon atom. That's the lightest of the hydrocarbons. And then they get heavier as you build up. Ethane, propane, those are all considered light ends, but as the molecules get more complex, they have more carbon in them, they are heavier indeed. So crude oil is a mixture of all these different molecules, and the trick is to separate them out. And of course, the thing we want the most of is gasoline. So we also want diesel and jet fuel and asphalt and propane and butane and so forth. But the trick is, how do we separate all those different components? And we do that based on the fact that each of those components has a different boiling point. So the point at the temperature at which the liquid becomes a gas, and we set up this distillation column that has different temperature levels, really. So what we're doing is we're heating up the crude oil and then using those boiling points to separate them out. So each of them has their own boiling points. You can see their kerosene and jet fuels is right around the middle, 350 to 450. The light ends like butane, methane, ethane are up less than 85. And then some of the naphthas are a little higher, I guess a little higher in the column and lower temperatures as well. So the heavy stuff like asphalt and lube oils and so forth have a much higher boiling point. They're at the bottom of the distillation column. So the distillation column is, again, has these different temperature levels, and what we're going to do is heat this mixture up, and there are a series of trays that are set up along in the column, and each of these trays allows the gas to come up through it because the trays have holes in them, and these trays are set up to be at different temperatures so that they're just below the boiling point of the particular component, so that component condenses there in the trays and then flows out. So there's a little bit more to it than that, but the point is that there are a number of trays throughout the distillation column, and the temperature at each one of those trays is very important for making sure that you pull out the different components from crude oil. Okay, then we have one more slide on that. So as the vapor rises through the trays, it cools and it comes out in these different stages. And again, very important to make that temperature measurement so that you're pulling out the right components at the right levels. Okay, so these vapors, they will condense at the trays based on the temperatures. The trays collects the fractions, and there's some more processing that follows after that. Now, I believe there's a handout, and you can see in your handout section there are 5 different handouts. One of those has this slide. I know it's a bit complex, but if you'd like to look at this slide and study it in more detail, it's in our handout section. Okay, so at this point, I'm going to turn it over to Ned.
Yeah, thank you, Tom. And let me change something here. So we did have in our previous presentation, temperature part 1, we did get a number of questions about infrared. So just going to touch on it today, not going to get into a whole lot of detail about how to use infrared and talk about emissivity and the different wavelengths and that sort of thing. But how do you calibrate an infrared sensor? And on this first bullet, you know, verification of accurate measurements can be challenging for any instrument. And in general, if it's something that's difficult or tricky, like a flow measurement, or in this case, infrared, can you find a way to just simply compare the field sensor against a similar sensor or device that you maintain in your shop or your laboratory? So the unit that stays in the shop or laboratory, it's not getting abused, it's not being exposed to extreme temperatures and weather. So it should not drift like a field sensor might. And specifically for infrared, one way to simulate temperature is, instead of a dry block like Roy's been using, is you can get hold of what's called a black body or a black body source. And ideally, it would be nice if you had 2 black bodies. You could set one to a low temperature and just let it sit there, and then set the other one to a higher temperature that represents your process and let it sit there. So it's always soaked out, reading a consistent temperature. So then for this type of test, you would remove the field sensor, bring it to where your black body is, and aim it at the black body. You would have your shop standard also pointing, and you'd be able to do a comparison of the temperatures. And if the field sensor's off, maybe all you have to do is clean the lens, and you'll see the temperature go up. But do keep in mind that this type of test is really a 1-to-1 accuracy or test uncertainty ratio. You're going to have sort of some wider latitude on how accurate you can be and when you should make an adjustment. But the idea would be is that if the shop sensor is reading a temperature, when you make an adjustment to that field unit, all your field units are going to be matched to your master in the shop, and it's going to allow you to make consistent, good measurements and try to get it back into good as new. There's some other things you can do with this shop sensor to make sure, you know, you might need to send it off every 6 months or something to be checked, but there's some other metrology practices that you can bring into play to make sure you're getting good, consistent results. And this transfer method, it can be used in other ways besides infrared. You could have a certified thermocouple, so maybe it's a type T thermocouple. Maybe you buy a batch of them, and you can compare any field T thermocouple to your master before you put it in service, or if you're pulling them, you can see if something's really off and do some troubleshooting. So, same thing for an RTD, you could use a PRT to make that comparison. So, and people are doing this with flow meters. You could have sort of a standard flow meter and compare that to your process flow meters. So just wanted to touch on infrared a little bit and how you maintain an infrared sensor and calibration. And this transfer method is another good practice you can employ. Okay, so I'm going to let Roy wrap up his presentation. Let's see where he's at on that temperature measurement he's trying to make.
Right. So you can see the calibrator I'm on my final test point, but first, I just flew in from New Orleans yesterday. And I was down there, and the food is always amazing. So I asked them, can you just give me a secret on how to make the food as amazing as you make it? And Mr. Elkins said, slap your mama. And I said, I will not slap my mother. And he says, no, slap your mama. I'm like, my wife? What? And then he hands me this. So this apparently is one of the secrets. To slap your mama, it's Cajun seasoning. So apparently I'm an idiot and I didn't know what he was talking about, but this is what it was. So I brought some home. Now back to my calibration. I've got my final test point. Let me hit continue. And as soon as I do this, you'll see the countdown. 5 seconds down here on the bottom. And then so I've got 0.047 degrees difference. And it's saying that it passed. My most significant error was negative 0.172 degrees Fahrenheit. So one comment about this is the first time that I ran this test, I had a tolerance of 0.5 degree and it failed. Let me arrow down and show you how it failed. On these test points, they were actually quite a bit off the zero. It's because I didn't give it enough delay. When the temperature dry block achieves its temperature, it beeps. That temperature is coming in, well, in this case, from the bottom underneath the insert, but there's usually a delay that you need to leave time so your temperature element can acclimate and come to the same temperature. So I needed to add in 3 to 5 minutes delay after the dry block achieved my temperature and before I actually accepted the test points. So if I wanted this to be a fully automatic calibration, I probably would have put in a 5-minute delay in between each test point, which would give me a very accurate line, which is what I'm seeing right here. Let me save these results. Let me go down one more. So here's the data, the numbers, that if I didn't have a documenting calibrator, I would write these down and then transfer them to my system, whether it be a spreadsheet or Access or something like that. Let me hit save. And I'll save this as both. I'll save it as both the as found and the as left. Hit my check mark. And now I'm done. Let me hit back here. And before I show you the calibration certificate, I want to show you something. At the most recent ISA Process and Safety Control Symposium, we did some calibrations of something else. And you can see that on the calibrator here. We calibrated a proximity probe. I didn't actually want to go into there. And we also calibrated a vibration transmitter. So we always want new input from you on what you want to see next in the next video set. What are those things that you're calibrating that you need a little extra help with, or something that needs to be demystified? And if it's this, let us know. We can do more info on vibration or proximity testing. So let me disconnect my calibrator. I'll bring over my software and just unload this real quick. So this is called temp element 1. Let me receive that. So I'm bringing over those test results, and if I wanted to see them electronically, this is it. And I'll right click and we'll show you a preview of the calibration certificate itself. So here we go. So this is our calibration certificate, and we calibrated the temperature element only. We didn't do a temperature loop, even though we could have. Here's the calibrator. The dry block itself was our calibration standard, so that's listed in the input as our standard. The calibrator is the standard for the output. Here's our graph, the raw data, followed by who did the calibration. So let me close that. Now, one more thing, we do have another video. I'm not going to show you this. I will not show you this, but it has me apparently drinking out of a Stormtrooper coffee mug, and Ned says something to make me spit my coffee out. But in order for you to know what that is, you have to go to YouTube. You have to check out that video, and it is within the first 2 minutes. And look at Ned. I mean, he just looks smug because he knows he's about to tell me something he shouldn't. Okay. So back with that, let me relinquish control. Ned, I'm going back to you.
All right, Roy, thank you very much. And yeah, every time I watch that video, I crack up.
Yeah, I bet you do.
All right, so folks, we are done. But we're going to have another Q&A session here. But before we open it up, let's just review what we've talked about in temperature. Back in September, we had part 1, and there is a link if you want to watch this webinar, and we're going to create a link for the one we're recording today, so you can review whatever we've talked about. But in part 1, if you haven't seen it, we did review sort of temperature basics. We looked at, temperature scales. We talked a little bit about thermocouple technology and RTD technology, and really stuck to just common applications with transmitters, and Roy made some demonstrations. So you can check that out. And then just to wrap up today, we tried to look at more complex applications. And when you look at heat exchanger, autoclave, or distillation, these different temperature type applications, try to relate what we showed today to things in your plant. That was the idea. An autoclave is very specialized, but I'm sure you have some batch processes where you need to have identical temperature measurements that impact your quality and other characteristics of your product. So, if you want to have consistent product coming off multiple lines, and temperature is one of those critical parameters, you need to be testing those probes and making them all read the same thing. And obviously, in the distillation column, those types of measurements can be very critical. So try to maybe relate, the different examples to what you're having to deal with. Also keep in mind that a loop approach can be very good in improving quality of measurements when it comes to temperature. And, I'm just a big proponent that you should pull that, if it's possible, pull that probe and put it in some type of temperature source, whether it's a bath or a dry block, and do an end-to-end checkout on some frequency. And today we wanted to show you the dry block as a tool. And, we talked about black bodies and using transfer standards. So there's other ways to check temperatures than just shooting ohms or millivolts into a transmitter. So I think we're going to bring Katie back online, and then we'll open it up for some questions.
All right, guys, I think you can hear and see me now. Excellent presentation. Before we go into the question and answer session, I just wanted to let you know, for any of you that are attending or thinking about attending the Power Generation Week 2015 event next week in Las Vegas, Beamex will have a booth there, number 2644. If you haven't registered already and you'd like to get into the exhibition hall only for some time, you can do so compliments of us. You can visit the coldgen.com website, which is part of Power Generation Week, and register entering that promo code. Okay, let's see if I can go ahead and switch to the next slide. And we'll go ahead and answer some questions. So we have a lot to get through, so I'm glad we wrapped up a few minutes ahead of time. So first question is, sorry, let me get back to it here. Is there any way to calibrate without removing the sensor from the process?
Yeah, Roy and I were talking about that earlier today. What you might have to do, you have to think about it, is could you install a thermal well, into your oven, vessel, whatever it is, so that you could walk up to that thermal well and stick an external probe in there and let it soak out a little bit and get a repeatable temperature measurement. It may not be exactly the same as the probe in the process, but if you check it over time, you should be able to see a consistent difference in temperature. If there's any way to, stick a probe into the process, that would also be, get a style probe with a handle that you can safely insert it into the process.
All right, thank you very much. The next question is, do we know how the DCS input card error, how do we know the DCS input card error? It is published by the DCS member.
Yes.
Yeah, I mean, Tom, how does Honeywell do that?
Yes, for any input card, there's either a D to A converter or an A to D converter, but there's some specifications for that from the DCS supplier.
Okay, next question. What will be the difference on calibrating or rearranging a temperature instrument?
I'm sorry, can you repeat that one, Katie?
The question is, what will be the difference on calibrating or rearranging a temperature instrument?
Okay, I can answer that if you want. So I always think of it this way, is calibrating is comparing an instrument to a known standard. So typically what you'll do is go up and to check out an instrument, and when you check it out, you're comparing its output to a known to a standard that you're assuming is the right reading, and if your temperature instrument is close enough to the standard, then no change is necessary. But if you go to check that instrument and it's out of tolerance compared to that standard, then you have to calibrate it. And in simple terms, the calibration means forcing that instrument to agree with that standard. Now, once an instrument's been calibrated, then you may want to range its output. So if, for example, a typical output is 4 to 20 milliamps, and if initially your 4 to 20 milliamps is scaled or ranged to be 0 to 100 degrees C, you may want to come back later on to rearrange it to say 0 to 150 degrees C equals 4 to 20 milliamps out. So in fact, calibration and ranging are different things. But a long time ago with pressure transmitters, they actually used to be the same thing, but we won't go there. But guys, you want to add to that?
No, I think that's pretty good. You know, when you're using the communicator and you rearrange it, you're not checking it against a traceable standard. You're just configuring. So they are different, different procedures.
True. Communicator has no ability to actually measure.
Katie, you're muted.
Oh, thank you. The next question is, how do we calibrate a temperature multiplexer?
You got to do them one channel at a time. I think the thing that Roy showed on the video with our colleague Mike, that field bus transmitter multiplexes, but you're checking, when you're calibrating, you're stepping through each channel one at a time. So you do your data acquisition or recording of readings fixed on a channel. Then once you've recorded, then you can move to the next channel and so on. So there's got to be a way to step through it to be able to calibrate it.
That's true.
Thank you, guys. Next question. The length of the cable between the thermocouple and PLC may give us a false measurement. How can we calculate the fault?
Having long thermocouple wire is not the best practice. My recommendation would be to put a transmitter as close to, if you have to have long wire, it would be better to put a transmitter close to the probe and then run 4 to 20 milliamps over. A thermocouple is like a little battery, is the way I was taught, and it's putting out a very low millivolts. It's less than 1 volt. 1,000 millivolts. And if you key a radio, you can make that noise from a radio can make a thermocouple signal just go crazy. So,
yeah, just to add to that, right, of course, the thermocouple signal is real low, susceptible to noise, and if it's run over a long distance, that's even more chance of having a problem. And I think going back to Ned's point about the end-to-end calibration is if you do an end-to-end calibration and there's noise on the thermocouple wire, that's probably not going to be repeatable, and I suspect that's going to show up in not being able to get successive calibrations accurate results. So if you do have noise, like Ned said, I think the answer is to put a transmitter in there to get a more robust 4 to 20 signal to go a longer distance.
True. And one other comment, you could actually test the wiring by simulating an actual millivolt reading or a thermocouple temperature equivalent with a standard with a calibrator. And then you could measure the output that you're actually getting, and thus you could see exactly what the offset is that you're experiencing.
All right. Next question. This is related to RSS and RMS again. Is RSS better than RMS as we summate errors from different sources?
wow. I guess, if I'm misstating RMS when I should be saying RSS, I stand corrected. Maybe the person asking that question could send me an email and possibly straighten me out. I don't know how to answer that question.
Good enough. Next one. How do we offset an error on a temperature transmitter after calibration?
How do you offset an error after calibration?
On the sensor itself and not an offset in the DCS.
I'm not sure you're saying that question, but I'll give it a go. So if you've checked the transmitter and in fact it needs to be calibrated, so it's been adjusted to agree with the standard. So once you've calibrated, it's reading correct when compared to the standard. And then if you want to put in an offset, I think the way to do an offset really is to set up the range to accommodate that offset. So if you have calibrated and it's calibrated correctly to read from 0 to 100 degrees C, that means when it sees those temperatures, it's going to in fact read those temperatures. And then if you want to have an offset, I think that's something that you could just incorporate by rearranging it. So if you want a 1 degree offset, you could range it from 1 to 101 degrees C.
I can give an example maybe that relates to the question and what Tom just said. We have a customer that has a batch process, and he's using RTDs to measure each line. He's got 5 lines essentially, and he was calibrating individual instruments. He was putting in, a good probe, had an accurate transmitter, and was checking the transmitter, and then had a PLC input. And he used a dry block to simulate a consistent temperature to the probes of those 5 lines. And he ended up putting a corrective offset into the PLC to make a consistent measurement. So if let's say the critical temperature was 150 degrees Fahrenheit, when he saw 150 degrees Fahrenheit with probe 1, and then he could insert probe 2 into the dry block, he'd see 150 degrees and so on. So that PLC would display 150 degrees for each line. So he basically sort of decalibrated the PLC to display true temperature, or as close to true temperature as he could get using the dry block. And it improved his quality by a huge factor. He was very, very happy because when he put in his set points, he was getting consistent results in his manufacturing process. So
I think that's a good use of an offset is when you have an instrument that cannot be adjusted. If you have a loop where you have a temperature probe and you have a transmitter, and the temperature probe is off by 0.1 degrees, you can fix that 0.1 degrees by doing a sensor trim inside that transmitter. So you do get a true reading back out to the DCS.
Exactly.
All right, thank you guys. The next question is, would you please talk a little bit about how the trend of temperature sensors is being smart sensors with Wi-Fi capability to go with smart plants and the Internet of Things?
I didn't get it, Katie. Read it again.
Would you please talk a little bit about how is the trend of temperature sensors being smart sensors with Wi-Fi capability to go with smart plants and the Internet of Things?
I can give that a go if you want. So I think what we're talking about is being able to add more temperature points without using Wi-Fi, adding more temperature points without necessarily having to add wiring, so that you're able to make more measurements and it doesn't cost so much to wire. Because sometimes people say it costs more to wire a transmitter than the actual cost of the transmitter. So now there are some wireless standards where you can connect temperature transmitters back to a gateway, and of course that saves, you save the money on wiring, and you're able to make more temperature measurements. So that would be my first reaction to that question. Ned or Roy, any thoughts on it?
Well, instead of connecting to thermocouple wire or RTD wire, you're going to treat that wireless sensor as an indicator. So you can still calibrate it by using a dry block or stimulating it with some type of temperature, and then verifying that what it's transmitting wirelessly, which is an indication, is accurate. And there should be a means to adjust them if they're off. So to me, that's how I would treat it, like a temperature indicator, and calibrate it as needed.
Right. So not having to wire things enables people to put out more temperature monitoring points than they would have in the past.
Okay, very good. We have a lot of people asking actually for the link for part 1. So the best way to find that would be to go to YouTube, so www.youtube.com, and in the search box at the top, type in how to calibrate temperature instruments, parentheses, part 1 in parentheses. So that'll probably be the easiest way to find it, and we'll send a link to it in the follow-up email as well. Okay, next question is, what is more accurate, an RTD or a thermocouple?
It's a RTD.
That was covered in part 1.
Yeah. So an RTD is typically a 0.1 degree C device, a thermocouple of plus or minus 1 degree C. That's just a rule of thumb.
Yep.
Okay, next question is, what is a digital temperature sensor?
It's what we just talked about with where it's maybe the wireless signal, where it's the A to D is occurring all at one place. So you're getting a digital signal out. It could be field bus as well.
Yeah, I'll add a little bit to that, I suppose. So the digital, the sensor itself is still going to be analog. So an RTD is going to be a resistor that changes resistance with temperature. A thermocouple is going to put out a millivolt signal. That's going to be analog. But when it gets into the transmitter, that analog signal is digitized, and we do all sorts of signal processing and calibrations and ranging and so forth in a digital format. And traditionally, people have then taken that digital signal and converted it back to analog to send 4 to 20 out. So that's, you're going from analog to digital, from digital back to analog, and people start to wonder if that makes much sense. But now with digital protocols, I mean, you can leave all that information in the digital form and send it out in the digital output, and that could be a HART, it could be DE, it could be field bus, Profibus, and I suppose even wireless would be a digital output as well. So when you did that last digital to analog conversion, of course there's error whenever you in something like a D to A, and so when you take that out, you remove some source of error. And digital gives you a lot of other capabilities as well, such as being able to transmit diagnostics. So you don't get that with analog. You can send out more than one variable, and just a lot of advantages to having digital communication.
All right, thank you. Next question. I have a project to automate a growing room for mushrooms. I need a very accurate measurement. Do I use PT100 or use another sensor, such as laser?
Is that laser? I would use an RTD. Maybe, are there going to be zones? Almost, think about what Tom said about autoclave. Do you need to have consistent temperature? If it's a large room, over in the corner, it needs to be the same temperature as the center of the room.
Yeah, it probably does.
Right. So the RTD would be very accurate, and I suppose, like these guys are saying, is you'd want to set them up in different areas to increase your chance of getting uniform temperature distribution.
All right, thank you. Next question is, what's the grade of effective of freedom and uncertainty of Beamex calibration? And I'll say that one again. What's the grade of effective of freedom and uncertainty of Beamex calibration?
Well, Beamex, if you look at our brochure for the MC6 that Roy was demonstrating today, we state uncertainty on our specifications, and we use a K factor of 2. So we state a 1-year stability with a 95% confidence level, and our statement includes the reference standard as well as hysteresis, nonlinearity, and other components. So we state a very conservative number. I would say just go to beamex.com and you can look at those numbers. Since we're talking about temperature, in general, our specs are unique by probe, but for a PT100 temperature probe, I believe we're somewhere around 0.06 degrees C. Typically, it's not as good when it's freezing. And then for thermocouples, it's kind of all over the place, but it's maybe kind of like Tom said, it's 0.6 instead of 0.06. We also sell and deliver reference probes. So when you connect our reference probe to our circuit that measures the RTD, and you use an ITS-90, Tom kind of touched on it, calendar Van Dusen or ITS-90 correction factor, we're seeing temperature accuracies as good as 0.006 degrees C. So that gets a little, mathematically the 006 is a little harder to justify than our uncertainty numbers, but maybe that gives you some insight into your question.
Okay, and looks like the last question we have is, how do you measure drift of an RTD?
You have to make measurements over some period of time. If it's a critical measurement, maybe you need to check it once every few weeks or once a month. Maybe if it's not so critical, say every 6 months or once a year. Typically, after you've made 3 cycles, you're going to see a pattern. Is it drifting to the north? Is it drifting south? Or is it pretty well flat? You're also going to have to consider what are ambient conditions. If you're checking it every 6 months, then that probably means you're checking it in the hottest day of the summer versus the coldest day in the winter. That could have an impact on the performance of an instrument. So usually after, 3 or more cycles, you're going to see a pattern, and you're going to be able to get into kind of a predictive mode. And if it's all over the place, if it's jumping up and down, then maybe you need to question your technology. Maybe what you're using is, you need to spend more money, or switch from a thermocouple to an RTD, or whatever you're trying to do. You guys have any other comments on that?
No.
Okay.
All right, well, that was our last question. With that, I'd like to go ahead and conclude the webinar, but before I do, a couple of minor announcements. If you need to contact the speakers later on, if a question comes up, their contact information was just there on the screen, and we'll send that to you once again in the follow-up email. ISA, the International Society of Automation, their symposiums have actually been announced for 2016, and there are several. Thank you, Ned. There's the Foods and Pharmaceutical Division, Process Control Symposium, a Power one, so be sure to check those out. There's lots of excellent presentations and speaker lineups for those events. Last thing would be to remind you to please take the survey that will pop up on your browser at the end of this webinar. We ask you, our audience, to guide us in the next topic. We want to present information on things that are relevant and things that you want to see. Finally, I'd like to thank our presenters so much for this excellent presentation and good discussion, and all the attendees out there who took the time to be with us today, and for all of the questions that you had. And hopefully we answered them well, and we hope to see you next time.